Okay, this lecture is to go over another type of filter. We'll call it right now the unity gain Butterworth low pass filter. So let's go back for a minute and discuss why we're unhappy with the filter design where we cascade a number of low pass filters together. So this is very comparable to an example that we did in class. In fact, it may be exactly the example we did in class. You're asked to design a fourth order low pass filter with a cutoff frequency of 500 Hertz and a passband gain of 10 to use 1 microfarad capacitors. So basically, we start out by cascading 4 prototype low pass filters. And the question is, okay, if we were to design these for 500 Hertz, then we have to figure out, if we want to cut off at 500 Hertz, we have to figure out what the design cutoff should be. So basically, we take 2 pi times 500 Hertz, and then we basically need to figure out, when we cascade 4 of these together, what factor do we get that would be the equivalent if we were going for the prototype cutoff of 1, what will we actually get if we do 4? And so you do that from this little equation right here, bottom of this page. And we did an example like this in class, so I'm going through it fairly quickly. Basically, this equation right here tells you for cascading in filters together, the cutoff of your filter will go from having its minus 3 dB point at 1, which is your prototype. But when you put 4 of them together, each time you cascade, you go higher or lower and lower in bandwidth, so you get a bigger effect. So for example, if you were trying to design a third order filter, you would put a 3 here, and that would give you some number. It looks like it's about 0.6, maybe 0.5. It would give you some number here. Basically, it's going to be a fraction, it's going to be a decimal. So like, let's say it's 0.58. So you would take 0.58 and you would take 1 over that, and that would be the cutoff that you'd actually design for, so that when it narrows the bandwidth because of cascading 3 of them together, you'll land on 1. So that's kind of the first thing. So basically then, that number for fourth order is 0.435. So if we were designing a prototype filter, we would have to take 1 and divide it by 0.435, which would give us a factor of like a little over 2. I think it's 2.2 something. But we also want to scale up to 500 Hertz. So first of all, when we scale, we won't be scaling from an initial frequency of 1. We'll be scaling from an initial frequency of 1 over 0.435. Then we'll have to use an additional scaling factor of 500 times 2 pi, and that's what will bump us up in order to get the perfect scaling factor to use to get our 500 Hertz. And so that number turns out to be 7222. And then in order to use those 1 microfarad capacitors, we'll need to find the resistor value, and we'll do that. So first of all, we figure out what magnitude scaling factor do we need to use those capacitors. So this is where you substitute for C and for the frequency and for the frequency scaling factor, and then you'll solve for the magnitude scaling factor. Once you get that, you scale your resistor up by that. So for this cascaded fourth order filter, we end up with something that looks like this, where 10 is our gain. And the circuit will be 4 stages of the unity gain filter, and then a single stage, which should give us a gain of 10. And is there an error in the book? It looks like maybe there is, because as you know, you have to have a ratio of 10, and that resistor in the feedback loop actually needs to be 1384. So really, that decimal point should be right there. Okay, so book error. So if you were to do a Bodie plot of that, it would look like this. Then, but the problem, okay, the problem is that this little transition region where you go from passband to cutoff, so here's 500. Okay, and it is indeed appears to be 3 dB down. But you'll notice how how kind of rounded this curve is. It comes way back here, almost a full order of magnitude. And we don't particularly love that. We'd like for it to do something more like this and have a more abrupt transition. But in order to do that, we're going to have to go to a different type of filter where the cutoff frequency is going to be independent of the filter order. So you can achieve that by figuring out what kind of transfer function you want, which would look like this. And then they kind of work backwards to figure out, okay, to get to here, what would my original transfer function have to look like? Okay, so in this case, the cutoff frequency is omega c radians per second, independent of the value of the filter order. And if n gets large enough, this denominator is always close to 1 when omega is less than omega c. So you're going to have that sharper kind of transition here that you want. The exponent of omega over omega c will always be even in this expression, which has some repercussions with regard to phase. So what we really want is a transfer function for our prototype. So this is for our 1 radian per second. We want a transfer function for that filter that has what we refer to as a Butterworth polynomial in the denominator. So for that first order filter, it's just going to look like a regular inverting amp low pass filter. For the second order filter, you want that polynomial to look like this. And once again, if you put that in to your Bodie plot, you'll find out that that gives you a cutoff at 1 and a little bit of a sharper attenuation, and then so on. So notice that the odd order Butterworth filter polynomials in the denominator all contain this s plus 1 term. That s plus 1 term is going to come from a single low-pass active filter, just like the ones we've already designed with the resistor at the input, a parallel resistor and capacitor in the feedback. Okay, so for odd, you will always have a stage like that. Even, you don't have that. For your even numbers, you're going to have, so for whatever n is, you're going to have n over 2 quadratic expressions. So what we now need to find out is what kind of circuit would give a transfer function with this kind of denominator. So let's look at that. This is a circuit that will provide you with a second order transfer function that makes it where we can get those Butterworth polynomials. So the first thing to do is to write a couple of node equations. Pretty sure we've got one here and one here. So you write those two node equations, and I think that's what it is anyway. Maybe this is it's a node. It's a node. And then you solve simultaneously so that you can get a transfer function that's equal to V out over Vn. Actually, that second one might be here. So you might have one here at VA and here at V out so that you get V out in your equation. So this is, if you solve the circuit using these two equations, this is what you get. And so you'll notice that you have a single value, you have two resistors, one value of R, and then you have a C1 and a C2. So in this particular kind of filter, we are not going to be able to pick one for all the values because we have two different capacitors, C1 and C2. So we're going to fall back on choosing one for R, and then we're going to let C1 and C2 say what the conditions need to be. Okay, now the key here is to look at the denominator your Miss equation. So this is your transfer function for the physical circuit. If we now go back to the previous little chart for a second order Butterworth, we'll notice that this is s squared, square root of 2s, and 1. So in order to choose the r's and c's correctly, this coefficient would have to be 1, which it is, and that's why I've all year long made such a big deal over the highest order term in s needs to have a coefficient in 1. Otherwise, your design can really get messed up. This one multiplies s, and if we go back, you see that in this case that is the square root of 2. And then this last one will equal to 1. And notice, by the way, for all of these quadratic formula, all of these quadratic terms, the constant is equal to 1. Okay, so that tells you that the square root of 2 has to equal 2 over RC1. So that is how you would do your design for a second order Butterworth filter. You set the prototype resistor value to be 1, and so that gives you 2 over C1, and then you let 2 over C1 be that middle term. Okay, once you solve for C1, you now know that this last term, this constant, has to be 1, and so making this constant 1, if R and C1 are known, then C2 is determined. So here's just an example of a fifth order Butterworth filter. So here is our Butterworth polynomial. Here is what the first filter will do, just a simple low-pass filter. Here is a first stage of our Butterworth filter, and here is a second stage of a different Butterworth filter. Notice that what multiplies s here are two different numbers. So we're going to have to do our design on this h of s twice. Once where 2 over RC1 is 0.618, and then again where 2 over RC1 is 1.618. So we'll get two full Butterworth circuits plus an inverting op-amp circuit. So eventually, where is my fifth order Butterworth? All I'm seeing is fourth. Okay, I guess that I don't have a schematic for that, but what it would look like is Butterworth cascaded with Butterworth cascaded with low pass. Then each one you would have to find the values of R and C. And then after that, what you have to do is you then have to do your frequency scaling so that you get your spec frequency. And after you have your frequency specification met, you have to meet the criteria on what you want the values of your R's and C's to be. So I'm going to stop the video here because I have an example, a handwritten example, where I do a design first using the cascaded low-pass filter and then using Butterworth filter and kind of show you how to step through that. And so I would rather pick up now with that particular filter design. Let me back through and make sure there's not actually, I don't have any schematic that shows those two Butterworth filters cascaded with that single filter. So that is probably in the textbook. Here's an example of a fourth order one. So this would be different. This is fourth order. So you see in the fourth order, if we go back to our table, for fourth order, we still have to do two Butterworth. The difference is it will not have a unity gain low pass filter also cascaded because it's just fourth order. So you get your filter out of just the two Butterworth. Once again, it's even, so it doesn't have that. So this one would be designed for one of the Butterworth polynomials, and this one for the other Butterworth polynomial, and then this one is just thrown in there to give you a gain if your gain is bigger than 1. All right. Now, if you design two identical fourth order filters, you use the same Cascade and Butterworth design, and you design the cutoff to be the same, then what you'll find is the Butterworth Bodie plot shows that you do get this sharper approach to your asymptotes in the transition region than from the identical cascaded filter. And this is actually more dramatic than it looks. So filters like this, because they are flatter in the passband and the approach to the asymptote is more abrupt, tend to be used in things like audio or other types of filters where you need to keep the amplification in the passband and you need to attenuate rather quickly in the cutoff band. So, and that's not an uncommon application. This is not, once again, a high Q filter. It's not a bandpass. You can design a Butterworth bandpass, in which case you would have to design both on the low pass and the high pass end, which would mean the only real difference would be that you would have a term in S. You would have a 0 in S in the numerator of your transfer function. So as an example, if we were to go back and we were doing a high pass filter, you know that the high pass is not 1 over S plus 1, it's S over S plus 1. So for the second order, it would be S squared over S squared plus square root of 2S plus 1, and so on. So you can design with two different cutoffs a bandpass filter using both a low pass and a high pass Butterworth cascaded together of whatever order you choose. So you could have a bandpass filter that was fourth order on the low pass end and the high pass end, meaning that you would have to design 4 of these, 2 for the low pass and 2 for the high pass. And what would be different is your cutoff, obviously, for the high pass would be below your cutoff for the low pass, so that you actually had that pass band. Okay, so that is the overview of the theory behind Butterworth filters. So I'm going to stop the video because basically we're where I want to be with background on the Butterworth filter. Although before we stop, since this hasn't taken up that much time, let's talk briefly about if you were asked to design a filter to meet certain specifications. So we've been throwing out numbers like, oh, we'll need a fourth order filter, or oh, we'll need a second order filter, without really talking about what that means. So what I want to look at are some general definitions that will talk a little bit about how we can make those specifications. So this is just a conventional low pass filter, and this is a plot of the asymptotes of the magnitude as a function of j omega, and obviously the pass band is in a lower frequency region for the low pass. The stop band is here when you're in the cutoff region, and then you have this transition area. And so we can use some definitions with some subscripts. The gain, so A represents gain at a specific point, and we'll choose point P and point S. So at omega P, we have some gain, and then at omega S, we also have some gain. And usually, if you're trying to specify a filter for a particular application, that is how the specification is given. People won't say, oh, we need a 60 dB per decade third order filter. They'll say, I want at the cutoff frequency to be at least a gain of 0 dB or 20 dB or whatever. Choose your number, choose your spec. But then at the second frequency, which is then specified, I want to be no higher than minus 45 dB. So you're given how much attenuation you want at a certain frequency. And then it's up to you to decide what filter order will actually meet that specification. So let's look at, I should have, I may not have. I don't have the actual follow-up on that, but in Wednesday's lecture in class, we will talk about how to actually make that, how to actually design that. And I'm also going to post a video from last semester where I go through that in more detail, just talking about given filter specifications, how would you then figure out what filter order you need. So I think I'll post that video, and then we will focus more in class on the examples that I have. Okay, so thank you, and that concludes this lecture on Butterworth filters until we do the example.